I'm happy to tell you now a little bit about the research that I'm doing and to describe how diamonds can be part of the quantum revolution we're living through. So what is the quantum revolution? We're actually, you might not know it, but you're living through a new revolution on how quantum aspects of nature and science can start affecting our everyday lives. And two examples of how that could happen are related to computing, to how quantum effects could contribute to faster and more powerful computing. The essence behind this digital computing idea is that we can store all information in the world by encoding it into the smallest units of information that we call bits, which are zeros and ones. With enough zeros and ones, we can say anything or encode anything. Now, these days, when we're entering the quantum revolution, people have realized that we can extend the idea of the bit of this little unit of information to a quantum bit. And a quantum bit, as opposed to this original standard bit, doesn't have to choose whether it's going to be 0 or 1. It can be both 0 and 1 at the same time. This is where we come in with our diamonds. So in my lab, we work with diamonds, not these very nice gems that you see on the screen. I can actually show you, I don't know if you can see this, a tiny piece of diamond that we work with. It looks very unimpressive. It's a kind of a square slab. It's slightly yellowish because it has a lot of defects in it. I'll tell you about the defects in a second. But it's still a very high-grade diamond. The diamond is made out of a nice arrangement of carbon atoms. The little blue circles represent these carbon atoms. But nothing, no material in nature is perfect. Everything has some defect in it, and diamond is no different. So every piece of diamond is going to have some impurity inside. For example, you could have a little nitrogen atom sitting in the lattice in a position where we should have found a carbon atom. It's an impurity. And this nitrogen atom sitting in there is actually a very common defect in diamond. This yellow slab of diamond that I showed you is yellow because it has quite a few nitrogens in it. Another very common defect that we encounter is a hole, a vacancy, which is marked with this V in the picture. Another common defect that can occur is the combination of these two. So we can have a nitrogen atom sitting instead of one of the carbon atoms, and then just a hole next to it. And this combination is a new type of defect with new properties, and it's called a Nitrogen-Vacancy defect, or NV for short. And this is the defect that we are interested in because it can be quantum. What do I mean? So first of all, this defect has a property that's called spin. It's essentially a little bit like a magnetic charge. So it feels magnetic fields and reacts to them. And you can imagine it as behaving like a compass needle. So it's as if we have a tiny compass needle within our diamond, an atomic-sized compass needle that will turn and react to an external magnetic field. So our NV defect is like a tiny compass needle sitting inside the diamond. But it's not a regular compass needle, it's quantum. What do I mean by the fact that it's a quantum compass needle? Well, you already know, right? A quantum system can be in two places or in two states at the same time. So if I think about this spin of my NV defect, it could be pointing up or it could be pointing down, but it doesn't have to choose because it's quantum. So actually, my NV defect can be pointing both up and down at the same time. And this is going to be the building block for our quantum computing device. This is going to be our quantum bit. So up is going to be 1, down is going to be 0, and our quantum compass needle can be pointing in both directions at the same time. And this is the essence of why we're interested in this defect and in diamond in general. Another thing that we're trying to push through in my lab, and I'll show it to you in a second, is to try to utilize the fact that diamond is transparent. And now we can actually measure the magnetic signals, the magnetic orientation of our little compass needles using light. So we're trying to build a small, compact MRI sensor that's actually going to sit at the end of a fiber like an endoscope and will allow us to go in and measure MRI signals very locally with high sensitivity in places where the regular big MRI machine can just not address or not sense. Okay, so here you can see one of our experiments running, and if you take a closer look, you can actually see a slab of diamond up here. This whole thing is essentially an optical microscope. It doesn't look like one, but we build them specifically for our experiments. And here we're using these NVs in diamond to measure and characterize magnetic signals out of new thin magnetic materials, potentially useful for applications such as spintronics and computing, and also to characterize the magnetic or quantum properties of these NV defects. So here we have an adapted setup similar to what you've seen before, but now we're trying to miniaturize everything and actually connect all of the optical components through an optical fiber with a diamond, tiny diamond at the end, to realize this endoscopic MRI sensor that I mentioned before. And this is a project that's being funded by the Israel Innovation Authority. Hopefully we'll be able to lead into a useful device to measure MRI signals that current existing MRI techniques are not sensitive enough to see. So this is my outlook that I'm leaving you with. The quantum revolution is here. In the longer term, 5 to 10 years, we're going to hear about huge impact coming from quantum computers that are going to allow us to compute things that today are just impossible to realize. And potentially in the shorter term, we're going to see quantum technologies using these intriguing aspects of quantum physics to enable better sensors, better MRIs, and hopefully much, much more.